So we've talked about the composition of functions before. We've talked about the idea that if we have a function f of x, right, and if we have a function g of x, right, what happens if we try to compose f of g of x, right? And what we get is basically a new function, right? And what do we do with that function? We basically take f and put in its argument g of x, right? And whatever g of x is, that could depend. And if you plug in the argument of f, we're gonna get a new function, f of g of x. So this is known as the composition of functions that I've described to you in a four-way method. Now the idea of a chain rule is that what if you have two functions composed with each other, right? And what if you take the differential of that with respect to x? Well, there's a general rule for this that you guys should try to understand. This rule basically says that what's going to happen is we're going to take the differential of g, right? But we know that inside g lies f of x, right? And we're basically going to differentiate g first, right? And g is obviously going to contain f of x. G prime is going to contain that, the differential of g. And after we're done with that, we're going to differentiate whatever is inside f dash of x. That's the underlying chain rule that can be applied to any particular situation. It's known as a chain rule because of, well, the obvious thing that's happening over here. You're basically taking the outer function, taking its differential first, and whatever remains inside, you're going to take its differential later on. So what I'm basically saying is, if we have a situation like we have the differential d by dy of sine y, we know that this has to be equal to cos y, right? We've talked about that rule previously. And if we have d by dx of x squared plus x plus 1, that is equal to 2 times x plus 1, because if you think about it, 2 just comes down and the coefficient of x turns out to be 1, and that gives us a 0. So if we get a 2x plus 1, that is giving us the differential of that. So we have two cases over here, right? What I'm going to try to do is find the differential of a composition of these functions, which is basically sine x squared plus x plus 1. What happens in this case? Well, let's try applying the chain rule. The idea is that we do the outer function first, right? And then move towards the inner function. So first, in an attempt to differentiate this, I'm going to do the outer function first, which is sine. So what happens when I differentiate sine? I get a cosine. But in this case, it doesn't really matter what's inside the cosine, right? Because I've differentiated the outer function first. So its argument is going to remain the same. However, once I'm done with the outer function, now is the time to talk about the inner function. So now I'm going to differentiate the inner function and multiply it by outside, right? That's going to be 2x plus 1. That, guys, is the chain rule right over there. You move from the left to the right, differentiating each function step by step. You converted the sine to cosine. You didn't really care what was inside, and you're going to put everything that was inside sine inside cosine as well, because you just differentiated sine. You differentiated nothing other than that. In the next step, whatever remains inside the bracket, that's going to be differentiated. So that's basically the chain rule in just one step. What if we were to nest this even further? So what I'm saying is, what if we had some weird kind of thing that says that we have like cos first, sine afterwards, and x squared plus x plus 1. I know it just looks very brutal, right? But it's just a one-step solution if you think about it. You're going to move from the left to the right, apply the chain rule as we move on. So this is basically, we're trying to find the differential of this, right? If we do that, we're going to first convert the cosine to well, whatever we can, because it's the outer function, right? Let's do that. Cos is converted to minus sine, which means the cos will be converted to minus sine, and whatever remains inside is going to remain inside. We don't really care. So sine, the inside argument in this particular case is sine of x squared plus x plus 1. It's huge, but I don't really care. It's an entire argument, and I'm not concerned with that. What I'm concerned with is converting cosine to minus sine. And once I'm done, now I'm going to move to the inner functions. The inner functions are sine x squared plus x plus 1. Now, if you think about it, the inner functions consist of two different functions. So first, in the inner function, I'm going to take care of sine before taking care of that. So now I'm going to differentiate this with, well, sine. So I get a cosine, but I don't really care what's in the middle, right? So it's going to give me x squared plus x plus 1. Now's the time to actually think about the function that's the most, well, with basically the deepest inside. So this is going to give me a 2x plus 1. So if you think about it, we've moved from the left to the right, making this a simpler problem as we've moved towards the right. This is a technique that's going to be very helpful to you guys. This appears to be very complicated, but it really isn't if you think about it for a while. It's just going to take a while to sink in. Hopefully when we'll be solving the questions from past papers, you will have a better understanding of how this can be asked, how this question can be tested in the coming examinations. So hopefully in the next video we're going to be talking about some higher derivatives, some very basic concepts, and the idea of implicit differentiation as well. That's going to be helpful to us slightly. So hoping to see you guys then.